And today we are here to start the lecture series of Mathematics 1. Chapter is Vector Calculus and today topic is Green's theorem in the plane. First of all, what is Green's theorem? A statement of the Green's theorem is if m of xy and n of xy and their partial derivative del m by del y and del n by del x are continuous in some region of R of the xy plane, bounded by the closed curve C, then over integration of bounded region over C m dx plus n dy equal to dual integration region R del n by del x minus del m by del y dx dy. So this is the original statement of the Green's theorem. What we do? What is the statement? M and n are the function and its partial derivative, it's continuous in the region of xy plane with the closed curve, and it is bounded with the closed curve. So we write as integration closed curve m dx n dy equal to dual integration of region R del n by del x minus del m by del y dx dy. Area of the plane region. Let A be the area of the plane region R bounded by the closed curve. We write as area equal to 1 by 2 integration closed contour x dy minus y dx. Example 1. Verify Green's theorem in plane for integration 3x square minus 8y square dx plus 4y minus 6xy dy, where C is the boundary of the region bounded, where x equal to 0, y equal to 0, x plus y equal to 1. Okay. Now we are taking one graph for the x equal to 0. This line is x equal to 0, this line is y equal to 0 and x plus y equal to 1. So we are taking these two lines are x plus y equal to 1. The point of intersection of the line y equal to 0 and x plus y equal to 1 obtain x equal to 1. So A equal to 1, 0 is the point of intersection. The point of intersection of the line x equal to 0 and x plus y 1 is obtained y equal to 1. So B equal to 0 to B0 to 1 is the point of intersection. Okay. So now we have m equal to 3x square minus 8y square, n equal to 4y minus 6xy. Del m by del y it is minus 16y and del n by del x is minus 6y. What is the Green's theorem? Green's theorem say that integration closed contour m dx plus n dy equal to, we have three paths, OA m dx to n dy, AB m dx to n dy plus BO m dx to n dy. That is equation 1. Now if we are taking OA path, so y equal to 0, so dy equal to 0. OA path, this is the OA path of this OA. Okay, OA path. So we take this y equal to 0, dy equal to 0 and x vary from 0 to 1. Integration m dx plus n dy over closed contour OA path 3x square minus 8y square mdx and dy. Okay, 0 to 1, 3x square dx. Why? Because y is 0, this y is 0, this y is 0. So we have only 3x dx. So answer is 3. So path of the OA of the region is 3. Second, now I am taking AB path. For the AB path, x plus y equal to 1, y equal to 1 minus x, dy equal to minus dx, and that time x varies to 1 to 0. Taking formula mdx plus ndy for the path of AB, it is mdx and dy. Put the value y equal to 1 minus x here, 1 minus x, 1 minus x, and 1 minus x. So we get 3x square minus 8, 1 minus x whole square plus 4, 1 minus x minus 6x, 1 minus x. For the dy, we take minus dx and interval is 0 to 1. 3x square 8, 1 minus x square minus 4x, 1 minus x plus 6x minus x square minus dx common we are taking and it's minus this here. Solve this integration, we get x cube 8 1 minus x cube by 3 4 1 minus x whole square by minus 2 6 x square by 2 minus x cube by 3 and interval is 1 to 0 because x is varies from 1 to 0. Now put the upper limit is 0 and minus lower limit is 1, we get 8 by 3 for the AB path. So answer of OA path is 3, AB path is 8 by 3. Now taking BO, x equal to 0, dx equal to 0 and that time y is varies from 1 to 0. Integration mdx and dy, mdx and dy, put the x equal to 0. If x equal to 0, then dx equal to 0, so we have only 4y formation, 4y dy, 4y square by 2. We are taking y square 0 to minus 1 and 1 to 0, upper limit minus lower limit, answer is minus 2. Substitute in equation 1. What is the equation 1? Equation 1 is 3 curve additions. Over integration mdx plus ndy 1 plus 8 by 3 minus 2. So answer is 5 by 3. Let R be the region bounded by the triangle OAB along the vertical strip PQ. Y varies from the 0 to 1 minus x and its region are x varies to 0 1. Del n by del x minus del m by del y dx dy over two regions 0 to 1, 0 to 1 minus x, minus 6y, minus 16y dy dx. What is del n by del x? Minus 6y, del m by del y, minus 16y. Integrate this with respect to x and y. We get y square by 2, 10 is common, 0 to 1 minus x. Put the upper limit minus lower limit, we get 1 minus x whole square. Again integrate this, we get 1 minus x whole cube upon minus 3. Put the upper limit minus lower limit, answer is 5 by 3. This is our equation 3. Now equation 2 and equation 3 have same answer. That means we have verified the Green's theorem. What we do? We take the 3 line formation OA to AB to BO and add this path of the area and verify this integration form of this is the Green's theorem statements and Answer from the Green's theorem statement and answer from this line integral formation statement are same. So we say that Green's theorem are verified. Evaluate over integration C 2xy minus x square dx x plus y square dy using Green's theorem, where y equal to x square and y square equal to x. By Green's theorem, over integration m dx plus n dy double integration region R del n by del x minus del m by del y dx dy is a statement of Green's theorem. Bounded region curve are y equal to x square and y square equal to x. Now m is 2xy minus x square and n is x plus y square. What is del m by del y? 2x. Del n by del x? 1. Along the horizontal strip PQ, x varies to y square to under root y region R and y is 0 to 1. Substituting in equation 1, we take 0 to 1 y square to under root y, 1 minus 2x dx dy. So integration 0 to 1 x minus x square y square to under root y dy. Put the upper limit minus lower limit, this integration in form of y. Integrate this again with respect to y. Put upper limit 1 and lower limit 0, we get 1 by 30 as the answer of the region. Thank you. If any query in the Green's theorem, please ask in the